Welcome back to the deep dive. Today, we're wrestling with a really fundamental piece of architecture, concurrency. How do you actually build systems that can handle, thousands of users at once without just freezing up?
Or corrupting data or crashing entirely. It's a huge challenge.
Absolutely. So our mission today is a deep dive into the, let's say, 4 main philosophies for server concurrency. If you're a programmer thinking, okay, what's next? Should I learn Rust for safety? Go for simplicity? Maybe stick with Java? Then, yeah, this is hopefully your quick guide to the trade-offs involved. But maybe first, why is this whole area still kind of a mess? Like, why can't we just spin up millions of OS threads in 2024 and, call it a day?
Yeah.
What actually breaks when your API gets slammed with traffic?
Well, it's fascinating because that choice you make, right, the concurrency model you pick, it's way more than just a technical detail. It's basically an architectural commitment. It sets the limits for your performance, your reliability, how much complexity your team has to juggle constantly. It's a big deal.
Right. It dictates a lot down the line.
Yeah.
Okay, so let's unpack the history a bit. We probably need to start with that original sin of early servers, which sounds simple, but was just deeply inefficient, blocking I/O.
Exactly. Think about those very first servers. They were sequential, right? Like a single cashier handling one person at a time.
One customer, yeah.
And if that customer needed something slow, maybe hitting a database, waiting on the network, the whole server thread just stopped, blocked, suspended.
And that's the massive waste, isn't it? You've got CPUs doing billions of things a second.
Yeah, billion.
Just sitting there, totally idle, for milliseconds, waiting for a slow disk or network packet.
Yeah.
Milliseconds is like an eternity for a CPU.
It really is. And that huge underutilization of really expensive hardware, well, that's what kicked off the whole quest for concurrency. We had to get those CPU cycles back.
Makes sense.
But moving away from that simple performance problem, it introduced this whole new world of correctness challenges. Suddenly you have multiple things happening at once, sharing the same memory. Things get chaotic fast.
Okay, what kind of chaos are we talking about?
Well, the big two are race conditions and deadlocks. These are the classic concurrency nightmares. But maybe first, quickly, concurrency versus parallelism. People mix these up all the time.
Good point. Yeah, let's clarify.
Concurrency is more about structure, how you design your program to handle multiple tasks, often by interleaving them. Think juggling. Parallelism is about actual simultaneous execution running tasks at the exact same instant, usually on multiple CPU cores.
Got it. So concurrency is managing many tasks. Parallelism is doing many tasks at once. Okay, back to the chaos then. Race conditions, the counter plus plus example is classic here.
Oh yeah, that innocent looking line. It's a trap because it's not one operation, it's really 3. Read the value, add 1 to it, write the new value back.
Read, increment, write.
And if the OS decides to switch threads right in the middle of that sequence, all bets are off. Thread A reads 5, grid B reads 5. They both calculate 6. They both write 6 foot. The correct answer should have been 7, but one update just gets lost.
Poof, corrupt data. And these bugs are notoriously hard to find because they depend on timing.
The worst kind of bugs. Non-deterministic. And then you have deadlocks. That's the mutual paralysis thing.
Where thread A have a lock B needs, and thread B has a lock A needs.
Exactly. And they both just wait forever. Total system gridlock.
So the fix that emerged was mutual exclusion, right? Using locks or mutexes.
Yeah, mutexes. The idea is to create a critical section of code, and the lock guarantees only one thread can be inside that section at any given time.
Simple concept.
But then you realize managing which locks to take in what order and making sure everyone on the team does it correctly every single time, it just introduces a whole new layer of complexity and potential errors. Lock management itself becomes a huge problem.
Okay, so given those fundamental problems blocking I/O waste, then race conditions and deadlocks from trying to fix it, how did server architectures actually evolve to handle scale? The first big step was thread per connection, right?
Right. That was kind of the first evolution. And it was clever because developers could keep writing code that looks sequential. You handle one request, start to finish. If you blocked on I/O.
The OS just swapped you out and ran another thread.
Exactly. The OS did the heavy lifting of scheduling, seemed elegant.
But then reality hit, the famous C10K problem. Handling 10,000 concurrent connections just didn't work.
Yeah, it hit a wall. And that failure came directly from the fact that operating system threads are, well, heavyweight. They're expensive.
Heavyweight how?
Memory.
Personally, memory, yeah, each thread needs its own stack space, which adds up. But the real killer was context switching overhead.
Ah, the bookkeeping.
Precisely. When you have thousands of these threads, the CPU starts spending more time saving the state of the thread it's pausing and loading the state of the thread it's resuming than actually running your application code.
So performance just tanks.
Utterly tanks.
Yeah.
Which led to the next evolution, the thread pool pattern.
Okay, so reusing threads instead of creating new ones all the time?
Yeah, you pre-spawn a limited number of worker threads and put incoming tasks in a queue. It definitely helped with the creation-destruction overhead, and it acted as a kind of resource control.
But it didn't solve the fundamental blocking issue, did it?
No, exactly. You still had the thread starvation problem. If all, say, 50 of your worker threads got stuck waiting on some slow downstream service.
The queue just backs up, new requests pile up, and eventually the server still hangs. You're still blocked.
Yep. The core problem remained. And this limitation, this is what really forced that radical shift in thinking. Model 2, the event-driven asynchronous paradigm. Stop waiting, start juggling.
Right, the philosophy totally flipped. Let's use that analogy you mentioned. The thread pool worker is like a chef just standing by the oven waiting.
Impatiently waiting, yeah. While the event-driven server is like this master chef. They've got 10 dishes going in 10 different ovens, timer set for everything, constantly prepping the next thing, never just standing still waiting for one specific dish to finish.
They're reacting to events, timers popping, ingredients arriving. Non-blocking I/O is their superpower.
Exactly. And the mechanism is typically a single event loop. This loop uses super efficient OS calls like Epol on Linux, Kqueue on BSDMA iOS, or IOCP on Windows.
Okay, these are ways to ask the OS, has anything happened on any of these thousands of connections without blocking?
Right. And the OS tells the loop efficiently, okay, connection 5 has data ready, connection 87 finished writing. The loop just handles these events one by one really quickly. You can manage thousands, tens of thousands of connections with minimal resources this way.
Amazing scalability for I/O-bound stuff then, like web servers, proxies.
Fantastic for that. Because you're mostly waiting on external things, the loop keeps moving. And this is the crucial trade-off, what happens if one of those tasks isn't waiting? What if it needs to do some heavy calculation?
If the master chef has to stop everything to spend an hour grinding flour by hand?
The whole kitchen stops. That single event loop gets blocked by the CPU-bound task. No other events get processed, no other connections get served. The entire server freezes.
So event loops are great for I/O, terrible if you have long-running CPU tasks. That tension, that must be why modern languages needed better ways to handle both I/O and CPU work efficiently, using all our cores without the C10K thread overhead.
Precisely. That history really shows why there's no single silver bullet, and it leads us directly to how today's major languages approach this, offering, like you said, 4 quite different philosophies.
Okay, let's break them down, starting with the old guard, the powerhouses, C and C++. Their philosophy seems to be about explicit control.
Absolutely. C++ gives you raw power, direct access. You use things like std.thread, low-level mutexes, condition variables, and importantly, RAII, resource acquisition, is initialization.
Right, RAII. We should probably explain that quickly. That C++ idiom where you tie resource management, like acquiring a lock, to an object's lifetime.
So when the lockguard object goes out of scope, its destructor automatically releases the mutex. It helps prevent forgetting to unlock.
Makes locking safer, but
But you're still deep in the trenches. You're dealing with manual memory management concerns alongside the concurrency complexities. Debugging a race condition in C++ that only shows up under heavy load once a week, it's arguably one of the hardest things in software.
yeah, the burden of correctness is entirely on you. Maximum power, maximum responsibility.
Pretty much. Okay, moving up the abstraction ladder, you get to Java. The philosophy here is more like managed abstraction.
Managed by the JVM, the Java Virtual Machine.
Right. Java offers the executor service framework, a whole java.util.concurrent package full of high-level tools. You submit tasks, the runtime manages thread pools, scheduling, all that stuff for you. Plus, you get memory safety thanks to the garbage collector, the GC.
That's huge. No manual memory mess, mature ecosystem, lots of libraries. What's the downside?
Well, the JVM itself has some overhead. And the GC, while amazing these days, can still cause those infamous stop-the-world pauses. For most apps, it's fine. But if you need absolutely consistent microsecond latency.
Like in high-frequency trading or something.
Yeah, even a tiny GC pause can be a problem. It's a trade-off for that safety and abstraction.
Okay, then we get to Rust. This feels like a really different beast. The philosophy is all about Compile time safety. Fearless concurrency is their tagline.
It is different. Rust aims for C++ speed, but with Java-like safety, crucially without a garbage collector. It achieves this through its unique ownership and borrowing rules enforced by the compiler.
A borrow checker.
The borrow checker, yeah. Along with traits like send and sync, which tell the compiler whether types are safe to transfer or share across threads, the compiler basically acts like an incredibly strict proofreader for your concurrent code.
So the payoff is massive. If your Rust code compiles, you have very strong guarantee that it's free from data races. That's the fearless part.
Exactly. Compile time safety nets are incredibly powerful. The challenge, getting it to compile in the first place.
Fighting the borrow checker.
That's the phrase you hear a lot. The learning curve can be steep, and the code sometimes feels verbose because you're explicitly proving safety to the compiler, but the payoff in correctness is undeniable.
All right, fourth philosophy, Golang. This one seems to flip the script again, focusing on communication instead of shared memory and locks.
Yeah, Go embraces the CSP model, communicating sequential processes. Tony Hoare's idea. The mantra is basically, don't communicate by sharing memory, share memory by communicating.
Okay, unpack CSP a bit. What does that mean in practice?
It means you think of your concurrent tasks, your Goroutines, as independent workers. They don't usually touch the same data directly. Instead, they pass messages back and forth over channels.
Like sending mail between offices rather than everyone editing the same shared spreadsheet.
That's a decent analogy, yeah. It forces a cleaner separation. You send data over a channel, the other Goroutine receives it. Ownership is implicitly transferred. It simplifies reasoning about who owns what and when.
And the mechanism is Goroutines, which aren't OS threads, right? They're much lighter.
Much, much lighter. They're managed by the Go runtime in user space. Tiny stacks, just a few kilobytes. This means Go can handle hundreds of thousands, even millions of concurrent Goroutines on typical hardware without the context-switching nightmare of OS threads. It's incredible for I/O-bound stuff.
Okay, sounds amazing for scalability and simplicity. What's the catch? Where do Go programs run into trouble?
Well, you trade one class of bugs for another. Instead of lock contention, you can get deadlocks on channels. One Goroutine waiting to send on a channel, another waiting to receive, but they're waiting on each other, or maybe nobody's listening.
Communication deadlock.
Right. And also, subtle Goroutine leaks. If you start a Goroutine and it blocks waiting for something that never happens, it just sits there forever, consuming a little bit of memory. Forget enough of those, and it adds up.
Okay, so leaks and channel deadlocks are the new things to watch out for.
Exactly. Different model, different potential pitfalls.
All right, we've covered 4 really distinct approaches. C++ is raw control, Java's managed world, Rust's compile time safety, and Go's communication focus. Now, the big question, how do you, the programmer listening, actually choose? It feels like it depends heavily on the job at hand.
Absolutely. It boils down to your workload's nature and your project's priorities. The first big split is your application primarily I/O bound or CPU bound?
Okay, find those quickly again.
I/O bound means you spend most of your time waiting for the network, for a database, for the disk. Think typical web APIs, microservices, that kind of thing. CPU bound means you're crunching numbers, doing heavy computations, rendering graphics, processing data.
Got it. So if you're primarily I/O bound, lots of waiting.
You need to handle potentially massive numbers of concurrent connections or tasks efficiently.
This sounds like Go's sweet spot.
It often is. Golang makes handling tons of concurrent I/O relatively simple and efficient right out of the box. The lightweight Goroutines and channels are built for this. Plus, the development velocity is usually pretty high.
Okay, but what if that I/O bound thing needs absolutely maximum performance or bulletproof security? Maybe it's critical infrastructure?
Then you'd probably look at Rust, specifically with an async runtime like Kqueue or async. You get that bare metal performance for I/O throughput, plus Rust's compile time safety guarantees, which are huge for security-sensitive stuff. More complex to write, perhaps, but maximum performance and safety.
Okay, so for I/O, go for speed of development and simplicity, Rust for ultimate performance and safety. Now, what about the other side? Primarily CPU-bound workloads.
Here, the game changes. You need raw processing power, minimal overhead, and the ability to effectively use multiple CPU cores for parallel computation.
This sounds like C++ or Rust territory.
Exactly. Rust and C++ compile down to native machine code with essentially zero runtime overhead stopping you from maxing out the CPU. They give you the fine-grained control needed to really optimize parallel algorithms.
So if it's pure number crunching, simulations, game engines...
They're often the top choices for raw speed.
But what about Java here? It's used for tons of complex backend systems.
Definitely don't count Java out, even for CPU-ish tasks. If your project involves really complex business logic, if you need access to that massive, mature Java ecosystem for libraries, monitoring, tooling, and if maybe ultra-low latency isn't the absolute top priority, but robustness and maintainability are, Java is still a very strong pragmatic choice. The JVM's JIT compiler is incredibly good these days, too.
Okay, that makes sense. It's about the whole picture. So let's try to summarize the trade-offs one last time for someone trying to decide, like a quick cheat sheet.
Okay, rough guide. If your absolute top priority is guaranteed safety and correctness against data races, look hard at Rust.
If you value developer productivity and simplicity, especially for highly concurrent I/O, Golang is probably your best bet.
If you need a massive ecosystem, enterprise features, and robustness, particularly for complex business applications, Java is likely the way to go.
And if you need the absolute fastest raw speed and fine-grained hardware control, and you're willing to manage the complexity, then C++, or maybe Rust again, is where you'll land.
That covers the main trade-offs, yeah.
So the core takeaway really isn't this language is best. It's more like you need to understand your specific problem, your constraints, and then pick the tool, the philosophy that fits best. It's all about the trade-offs.
Exactly. There's no dogma here, or there shouldn't be. It's engineering making informed choices based on requirements. And interestingly, you see the languages borrowing ideas from each other now.
Like Java's Project Loom.
Precisely. Project Loom introduces virtual threads to the JVM. They're lightweight user space threads, very much inspired by Go's Goroutines. It shows how successful that model was. And now Java gets similar benefits for I/O concurrency within its existing ecosystem.
So the lines are blurring a bit. The future might be more hybrid, pulling the best ideas together. But understanding these core historical differences still seems crucial for making good decisions today.
Absolutely. It gives you the context for why things are the way they are.
Okay, so maybe a final thought to leave people with. The next time you write, I don't know, even a simple loop, just pause and think. What happens if you slap a Go keyword in front of that function? Call and go. Or std.thread.spawn in C++ or Rust. Or wrap it in an executor service.submit in Java.
Yeah, what fundamental assumptions are you making right there about how resources are shared, about who guarantees safety, about how blocking is handled? Understanding the philosophy embedded in your language's concurrency tools. That's key to building robust systems. What invisible contract are you signing?